I mean,
Okay, here was the
if
wired
if
piece.
every scientist ignored whatever other scientist was working on, that would not work at all. But if we are just a pack of dogs, then that's not going to work either. So
yeah, well, we've seen this playing out in physics over the past few decades, where so many people have piled into the standard model that it is nearly career ending to study alternative versions of physics. I mean, there's a little loosening up just over the past few years of people willing to talk about other things, but
well, the thing is, they haven't found anything that's an exception to the standard model at the Large Hadron Collider yet. So
they also haven't found dark matter yet either. Or dark
right.
energy.
Well, but I mean, and that is an active area of research. You can do well in dark matter, especially if you're in observational dark matter.
Observations of nothing. Yes.
Well, I mean, it's not nothing. We know it's there, but it just don't know how to observe it. And so
what if the expansion was our kind of like the shrinking of our sphere of observation?
I don't understand how that works, because it's not shrinking, it's expanding.
If your area of observation is being reduced, and there's something that you're looking at through this relative to your ability to observe, that thing outside would appear to be getting larger compared to this shrinking aperture.
I still don't understand.
Well, if your aperture gets smaller relative to something...
What do you mean by aperture?
Something that you're observing through.
Uh-huh. What are we observing through?
An aperture.
Yeah,
Our eyeballs.
It's a hypothetical construct to illustrate the point.
I don't get it. Sorry.
It's like the widget in a factory. It's a fictional product that the factory sells. The aperture is a fictional mechanism through which we observe.
Well,
it's like the widget of a factory in business.
Take a for instance and say some actual artifact. Let's say the 200-inch Mount Wilson telescope is the aperture through which we're viewing the universe. Then where do we go from there then?
Well, no, I would do it simpler. I would say, okay, this wall behind me is the thing we're observing.
Okay.
And our area, our measurement is this card. Okay? So there's a certain number of this card when we view the wall through, let's say this was hollow and we could see through it, there would be a certain size we would measure looking through this. Now, if we took that and then...
Wait, what are we measuring the size of? The wall or the card?
We're
looking at the wall through the card.
Through the card, like this was transparent. Let's say this is the thing that we can see. This is
but what are we measuring the size of?
The wall.
The wall. Okay.
We're not measuring this because this represents our ability to observe.
But wouldn't it be smart to measure that first?
How would you measure it?
With a ruler.
But that's if your ruler is shrinking, how would you know?
If my ruler is shrinking, well, if my ruler is shrinking, I would know that the card. I don't get it at all. Sorry, you're losing me.
Okay, let's say this is a ruler.
Okay.
This thing, and this is our standard of measure.
Uh-huh.
Okay. Now, if our standard of measure is shrinking, the measurement we're going to get for the wall will be increasing. Right?
Why would it shrink and not the wall shrink?
Doesn't matter. Let's just agree that, do we agree that if this is shrinking, the measurement of the wall would increase?
No, you haven't defined shrinking.
Only if everything was shrinking along with it at the same time at the same rate. So the card is the aperture that we're viewing is through is shrinking. We are shrinking, and everything around us that we can observe is shrinking. Then we couldn't tell the difference between our shrinking and the rest of the universe getting big. Is that what you're saying?
Well, I don't know why. I don't know that it's required for like us to be shrinking. Maybe that would be sensible.
Well, because if the card were shrinking and we weren't shrinking, we could measure it.
Yeah.
Because we'd have other items that we could use to compare it to and say, wow.
All measurements are comparisons.
All measurements are comparisons.
The first measuring instrument we have is the human body, and then we always carry that around with us. Whether we say a horse is 10 hands tall, or a yard is from the nose to the tip of our finger, or something like that.
Well, I like to be more conservative because, and I like to stick to observation rather than like make an appeal to. Where science and really any information system, and this is about the only thing that I think that I can say I have added to the conversation is that I think it's fair to call physics specifically an information system. It's a structured process by which we hope to make better decisions and generate knowledge from data. So we get this data, we turn it into information, and then it graduates at some point, which can be debatable, into knowledge. So where we have had long-standing problems in science and just in business information systems or other kinds of information systems, the problem almost every time has been an unexamined assumption that has turned out to be wrong. And it looked right, and we thought it was right, but it turned out to be wrong. And so if you look at the big changes in science, like the development of heliocentrism or Darwinian evolution, the differences that we observed in, let's say, living animals for Darwinism, we observed these things, but in the post-Darwinian model, it turned out that the assumption of that we observed these separate things, it turned out to be refuted and recategorized in a particular way in the new model, in the evolutionary model. And the same thing going from geocentrism to heliocentrism. We watched the sun moving through the sky, and then this was recategorized as an observational consequence of us being on the rotating planet's surface. Okay? So it's a change in observation, and what we've got with physics and the inability for now over well over 100 years with relativity to resolve these anomalies. The reason that kind of thing happens, especially when you've got the largest, most expensive instruments that have ever been constructed, and the finest, best educated minds in the world working on this problem, and they haven't solved it. There's an assumption.
Which problem was that?
Uniting quantum mechanics and relativity.
Well, see, the problem is that the instruments, no instrument observes both domains. You have really great telescopes that can observe at the large, and they confirm general relativity down to the gnat's ass, right? And then you have instruments like the Large Hadron Collider, which can't see any general relativistic effects at all, right? But they confirm the standard model down to the gnat's ass. We don't. right now it's really, really a struggle to find something that can do both. And really, the only place where you really get both is at the very early universe. And
well, why do you need one instrument that looks at both things? I don't understand.
Well,
that.
if you want to confirm, if you want to do an observation that confirms quantum gravity or informs quantum gravity, then where do you get that observation?
I don't know. I had not proposed getting an observation of quantum gravity.
Yeah, well, the thing is, if you can't test it, what is it?
Well, it's kind of like a gene. The concept of a gene. It was around for decades, if not more than a century. People knew there was some agent of heredity. They didn't know what it was, but they had. I mean, and they didn't need to observe it directly to know it was there. Much like in Sagan's book, Demon Haunted World, where he talks about, if you have an android in a room, you can tell it's responding to light by certain behaviors, and you don't need to actually have evidence that it's got detectors on it, or you don't need to examine it to be able to tell from its behavior.
Yeah, but the problem
things.
is, where's the anomaly? That's my question.
The anomaly is that when the mathematics have been put together, the functions go crazy.
Okay, so it's not an observed anomaly. It's just we have two mathematical models that don't play nice together.
And the idea has been that if we can get higher and higher energies at these and better looks at these subatomic particles, we can get answers. If we observe the dark energy more carefully, something will come out of the data at us, and that has happened in the past. But at some point, that stops happening, and that's what happened in the geocentric versus heliocentric revolution, and
that's also a very unusual way for scientific discoveries to happen. Much more frequently, people work out the theory and then try to test the theory rather than running a bunch of observations and see if something pops out at you, which is what experimentalists, have as a view of theory.
Right. I would agree that's the overwhelming majority. Most, and it's what I guess it was Kuhn called puzzle solving science.
Right.
Which he said is
standard science, which is
normal science.
Puzzle solving.
Normal science.
Yeah.
Of the puzzle solving variety. But in this case, and from the LHC is, you can't. The superlatives aren't strong enough to give it to represent it fairly in all its magnificence. On the other hand, it represents a profound failure in that all this investment was made to determine which of the predicted masses for the Higgs boson would be discovered. And one of them led to supersymmetry, and one of them led to multiverses. And this was the core question that the instrument was built to resolve. And when they fired the thing up, the result was right in the middle of the two gigavolt, giga electron volt measurements that they had said they were going to get one or the other. And there are people in the film. There was this film, Particle Fever.
Yeah,
have we talked about that?
I recommended it once here as my recommendation on the Unseen podcast.
Did you know that I'm in that in a couple of places?
No, I didn't know that. I have a copy of it, but I didn't notice you in it.
I actually shot an interview in the where I was trying to get this underlying assumption thing into the film, and it was on the cutting. It ended up on the cutting room floor, and the only bit of me in that film is where Weinberg's giving a presentation at the Wheeler Opera House in Aspen, and I'm sitting there. I'm sitting there in the audience, just like looking. You can see my bald head. That's it. Anyway, if this were an information system that I was in charge of, and I was going to get to me, I think the most vital thing that we could do to make this research productive is avoid referring to, especially the fundamental concepts. It's particular concepts within a cognitive frame get altered in a particular way. And here's a great book on it. There we go. Cognitive Structure of Scientific Revolutions.
I think you've recommended that in the past.
Yeah, I have. And these guys have gone through and looked at how problems like the current. I think in the future they will look back at this incompatibility that has gone on for so long and been the subject of so much expensive and really good investigation, and they will say, well, this is the kind of crisis that was the analogous to the Darwinian revolution, the geocentric to heliocentric revolution, and in the thing that it seems to me would have been most productive for people at that time is to avoid saying space or time or these other fundamental concepts, and say our observation of space, our observation of time, our observation of in the biological instance, our observation of species, and it would have helped them take a more cautious approach to assumptions that just were kind of built into the way they thought about things, and that seems to be the case now.
Well, no, I think they did all that thinking, Buck, and special relativity is baked into quantum field theory. And
I would push back and I would say, show me the physicist who doesn't describe dimensions in integers.
Well, yeah, but I mean, show me the evidence that that's not the case.
Show me the theory that can represent, space and time and matter that is not a mathematicized natural science theory, and I'll show you something that's not going to be much good to anybody.
I'm not saying not mathematized. I'm just saying that if it strikes me as very unlikely that the fundamental reality in which of our universe, given its size relative to creatures of our relative significance, which is probably pretty low, if the fundamental aspects of reality just happen to correspond to a monkey's favorite or an ape's favorite way of counting things on their digits, that would have been a hell of a coincidence, wouldn't it?
Okay, fine.
Well,
do the calculation. Well, the problem is, Buck, we can do the damn calculation and we get the right answer. We get the answer that we observe. So, I mean, you have to show that there's something wrong with that. You've got to find the anomaly, and you've not found it. No one's found it.
To say there's something wrong, I have to find the anomaly?
Yes.
No, I can say these cars crashed and people died. I don't have to know I don't have to know how the crash occurred.
I don't understand the analogy at all.
Well, you're saying that to say that there's a there's a problem with the information system, I have to know what the anomaly is, and I can have indications of problems without knowing the root cause.
No, I'm not asking for the root cause. I'm saying what is it that we can calculate that we're calculating wrong?
Okay.
The answer is nobody knows anything. There may be something, but we haven't found it yet.
Well, I guess it kind of depends on what you mean by wrong. Like, you can calculate something in binary by hand.
So, yeah, I could. It'd be tedious, but yeah, I could.
Very tedious, yeah.
Right.
I have done that, by the way.
Yeah. And so practical considerations dictate, or practical constraints dictate, that if you're doing something that way, you're not going to be able to do calculations if you used a more efficient method. That's better. It's a more effective representation for the type of answer that you're after, right?
No, I don't get it.
Okay.
I can represent everything in binary.
And
I have computers that can do calculations really well in binary.
But can you really, like, can you multiply 2 million by 444 in binary?
Yes.
Really?
Yes. Sure.
By hand?
By hand? Yeah, I could. It'd be tedious, but sure, I could do it.
You need a very large piece of graph paper so you keep your columns straight.
And how long would this take you?
10
How
minutes.
many hours? Really?
Minutes. Yeah. But I have a computer that can do it in microseconds, so why would I care?
Right. You wouldn't care, and you wouldn't do it in binary.
No, the computer does it in binary. It represents all numbers in binary.
Yeah, but I'm not talking about your computer. I'm saying you. I'm not saying your computer does it in binary. I'm saying you do it in binary.
We do it in monkey digits because we evolved that way, and we program our computers to spit the binary back at us in monkey digits because that makes sense to us. We've got 10 figures, so we use a base 10 numeration system.
Yeah, that's all been very well worked out. There's no issues.
Yeah, there's not much of an issue there.
Okay, but nature doesn't appear to do this. Nature doesn't appear to use integers for much.
Okay.
So
therefore,
it seems like there's a bit of a mismatch between the standard tools that we use to represent things like dimensions and what we actually observe in nature.
Oh, no, you're saying no.
Well, do you have a better formalism than that which exists? I mean, the formalisms we have are imperfect. As I just said earlier, all models are wrong, but some models are helpful.
Right.
So, the formalisms we have for treating dimension mathematically, they work pretty damned good. And they not only do they work good, but they outstrip human intuition by a long distance. You can make a calculation on paper on a computer, and then if you've got what it takes, you can translate it back into intuitive terms, and then your monkey brain says, "Oh, wow, that works." And
works for what?
Well, it gives you a new idea that you couldn't. It was too difficult for intuition. So you run it through a formalism, and the formalism gives you an idea that then you can take and you can run with that in your monkey brain, and you can make progress that you wouldn't have made without the formalism.
Okay, yeah,
that's why we apply imperfect numbers to an imperfect world, and it works well enough to give us what we've got in terms of quantum theory, relativity, general relativity. We can't put it all together yet. Yes, that's true. There are anomalies everywhere out there. We don't even know why galaxies rotate the way we do. We don't know, like you said earlier, why when there were two theories for for particle physics why we got the value right in the middle instead of getting the value for multiverses or for supersymmetry. So we don't know what's going on there, but we know a lot, especially in compared to what we knew, say, 2,000 years ago, when we knew very little about describing the universe in a helpful way, where we can transfer from the science to the technology, to the engineering, and have an industrial solution that keeps 7.5 billion people alive because they're all eating and they're all drinking and they're all being housed and clothed.
Mm-hmm. Yeah, and I agree. I agree with everything you just said. I'm not convinced. I mean, if we're going to compare that, though, I think the I don't know what the price tag on the LHC was, but I imagine that that money could have fed and clothed a lot of people who needed it.
Practical question. What if you were the one calling the shot? How would you have spent the money that was spent on the LHC?
I would have probably supported development and research in geometries that use that accommodate integer dimensions as a subset of the real number line.
Mathematicians are cheap. What kind of hardware would you have sponsored?
Why?
Okay, well, here it says.
I'm not sure that's my first priority. So
okay,
why?
Well, hold on a second. According to an article in Forbes,
Mm-hmm.
the total cost of finding the Higgs boson was $13.25 billion.
Okay.
So say you're already going to richly endow the best scholars in mathematics at all the world's major universities. They're going to have money coming out their ears. I mean, they're going to be driving Ferraris and drinking champagne and riding in limos. So they've got plenty of money, and you've only used up a very small part of your $13.25 billion. But you've got this budget to spend on science. You want to get the biggest bang for the buck, whether it be theoretically, experimentally, or practically in terms of industrial products.
Mm-hmm.
How would you spend the $13 billion?
Well, as I said, I would want to support what I consider stronger mathematics, which is why I think I think this Furey and her ilk are sort of barking up the, if not the right tree, a better tree with stronger mathematics, similar to the advantage of trying to do binary by hand versus punching it into your computer. And also I think this would open up, like integer dimensions are great for representing things that I see behind you, like the edges of your calendar there, very well represented by lines, the front of the front surface very well represented by a plane. As long as you don't look too close, for all practical purposes, that 2 dimensions on a sheet of paper is it's efficient. It's got all sorts of pragmatic virtues. Yeah. Okay. He's got a call.
Yeah. Well, I mean, I still don't get it, Buck. I mean, we don't have any data that tells us that we need non-integer dimensions.
Do we have any data that tells us we need science?
Yes.
Okay.
Yeah, but what would you understand without it?
Well, I for the overwhelming majority of our existence, we became the dominant species.
Okay,
science
so
is
we're
pretty
smarter.
recent.
We're smarter than the other monkeys, but what else would we understand without it? You're saying we don't need science? Is that your claim?
No, I'm saying that.
Why are you asking me if we need science then? You're trying to jump me? You failed.
I'm saying that the demand for that kind of justification is kind of a strange request.
No, I'm saying, why would you develop a mathematical model for something that you already have mathematical models for that have no anomalies?
Well, you might do so just because it was an interesting puzzle, and you're doing it for the pure pleasure of investigating.
Okay, I'll buy that. You're doing it because it's fun.
You love it, yeah. And you might derive an insight that you didn't derive from doing it the familiar way. I'm not saying that scientific discoveries are routinely arrived at this way, but there are people. I mean, there are people who study all kinds of things that to outsiders seem very peculiar, and sometimes these people have marvelous insights because of their unusual way of looking at problems.
Right, and there are lots of mathematicians looking and physicists looking at out of the box ideas.
Yes, there are. There
are. Once you have tenure, you can look at anything you want, right?
There's never been more physicists or mathematicians alive in the history of the planet than there are at the present time.
And there are unsolved problems, and there are and there's a lot of smart people looking at those, and I applaud that. But what I'm saying is, there's no reason to pick a particular fight unless you can motivate it, right? And you need some kind of motivation to say, oh, well, this can't be the right answer.
You can always find a pretext. I mean, just if you want to start a war, you can send somebody over on the other side and have them shoot at you, and well, we've got a reason to go to war now. And it's the same thing in science. Every science has anomalies in it, and most people look past the anomalies that everybody's used to. They just accept them. And if somebody wants to come along and declare war on you,
tell me about chemistry.
I don't know enough about the history of chemistry to be able to tell you what anomalies are in the subject.
But this is an example of something that we think is a genuine science, but it has been mostly reduced to physics. Like particle physics.
Well, and so from that
standpoint, So from that standpoint, it's not really doing much. Fundamental research of that type. It's kind of that, that's kind of like a classic example of something. Well, if we say that a genuine science has to have unanswered questions it's working on, it's not that certain that traditional chemistry anyway is still in that game. So that's one of the cases where we want to make sure we don't make our demarcation criteria too strict. And just to cut to the chase on that, what they've done to get around this is they've said, well, different sciences can actually have different criteria. So the demarcation criteria problem, the demarcation problem, depends on which science you're talking about.
Well, I don't think that's a big problem for chemistry at all. That they use a lot of atomic physics.
I don't think anybody does.
They have there's a lot of molecular structures that aren't known, and there's also a lot of techniques that they need to develop for synthesizing other molecules, and things like protein folding are very, very complex. So it's just when you get above the level of atoms, everything gets so complicated that there's tremendous amount of things to explore. Freeman Dyson wrote about that in one of his books. He said, there's the mountain where physics and mathematics live, and there's the jungle below the mountain. And the jungle is actually more interesting than the mountain.
I thought of an example of chemistry where something is not fully understood, and that's the notorious cold fusion experiment. Which there's still no concept, what people now call LENR, low energy nuclear reactions.
Yeah, it's controversial whether that's really real
it's
or not.
controversial, but the fact that there is a controversy and that chemists do not have a bottom, rock bottom. Well, this is what happened. This is why this thing got warmer for a while, and this is exactly the chemical process that took place. That shows that there are still unresolved questions in chemistry.
Maybe. I mean, I'm
Yeah.
not well enough versed enough in that. There seemed to be a lot of mistakes made early on.
I didn't even know that was still I didn't even know that there was still any controversy.
There are people who still study low energy nuclear reactions.
The problem is that when you start looking at things like gamma rays and neutrons, those measurements are really hard to do, and chemists don't have any expertise in doing them, so it's kind of, the problem is you're sort of the borderline of two disciplines. And I don't think any of the physicists believe that there was anything to that.
We can distinguish here different levels of observation and different levels of theory. So, like you say, the physicists might not have had much of a truck with it, but there might be still things that you would say on a chemical level about it. And just like Buck said earlier, that chemistry can be reduced to physics, but sometimes physics is not the most economical language to use to talk about things. Sometimes when you talk about chemical reactions, you want to talk about the chemicals, and sometimes when you're talking about biochemistry, I was thinking the other day, I haven't worked this out completely, but how complicated would it be to explain natural selection in terms of what's going on chemically? Not talking about macromolecules or things that are alive. I mean, natural selection is a very easy idea once you grasp it at the biological level or the evolutionary level. But trying to formulate it in chemistry terms, much less formulating in physics, would be really, I think, beastly.
It would be ridiculous. I think you'd fail anyway.
So even if you apply the principle of parsimony, just like Buck was saying that it could be different demarcation standards for different sciences, there might be different parsimonious standards for different sciences. So talking about one thing in terms of chemistry might work well, another thing in terms of physics might work well, and another thing in terms of biology might work well. So they might be reducible in an ideal context, but in practical fact, our monkey brain needs these human level concepts of a reasonable degree of simplicity.
That's what Dan Dennett calls cranes, right? Cranes take you from one level of description to the other. It's like, we can understand the basics of biology in terms of biochemistry. We can understand the basics of biochemistry in terms of atomic theory, but each level is so much more complex than the other one that it needs its own level of description. And from biochemistry, you go to cell biology, and from cell biology, you go to tissues and organs and so on. And what actually tells you whether an organism is going to be selected for or against has to do with its behavior, and its environment, its competitors, its population, things that are...
It's ecology, in short.
Yeah, right. Way, way above the level of atomic theory. And
I wasn't familiar with Dummett's terminology, but other people call those levels of emergent complexity.
Yeah, in his book, Darwin's Dangerous Idea, which I recommend strongly, he used...
Yeah, I read it some time ago. It's a great book.
He uses the phrase cranes and skyhooks. And cranes are fine in science, skyhooks are not. And all I can say is just go read that book. It's defines it very clearly. A crane is basically using a careful, patient approach for building from one level of complexity to the other. But a skyhook takes you from low level up to high level in one move.
And here we can tie it up to what I was saying earlier in this conversation. A crane then is a constructive form of reasoning, and a skyhook is a non-constructive form of reasoning. And that's why people object so strongly about non-constructive forms of reasoning, because they appear like a skyhook or like a miracle.
A miracle, or what Dennett calls wonder tissue.
But there are forms of non-constructive reasoning that we really can't get by without. And I've argued in several blog posts that we are profoundly non-constructive creatures because we are human beings living inside a universe and trying to make sense of it from the inside and not being able to stand outside and observe and see how it all works. We have to try to figure it from the inside out.
Well, you know what? I think we're going to leave it at that.
Seems like a good stopping point.
Because, well, it's been a good discussion, but I'd like to point out that what we are going to start doing now with the Unseen podcast is each recording session is intended to result in 2 episodes. We're going to try to make it into a commute-friendly duration, maybe 30, 40 minutes, something like that. Well, probably more like 40 minutes. So it doesn't eat up your entire week or your entire 2 weeks until the next one comes out. So, and we'll also try to release each episode on, right now the target is Sunday at noon Eastern time. So it's ready for your week. You can decide, you can look at the show notes and decide, is that something I want to queue up or not? And hopefully the answer will be yes. And we'll break it into a couple of pieces so you can have one week, one the other week. We're still going to try to have recording sessions every 2 weeks. This is a bad time of year because it's right before Labor Day in the U.S. and school starts next week in much of the U.S. And so a lot of families are on vacation or, out with their kids. I will be doing that this week, weather permitting, myself this weekend. So that's I have 2 kids starting one starting high school next Tuesday, and one is a senior at the same high school. So it's going to be pretty dramatic next week. And I can understand why some people will not want to be here tonight, but we will continue this in 2 weeks, and again in 2 weeks after that. And so thanks for listening, and good night. This has been the Unseen Podcast, the unscripted, uncut, and open participation podcast from Dream of the Open Channel. For more information, including show notes for this episode, please visit unseenpodcast.com. You can also follow us on Twitter @PodcastUnseen. If you are interested in joining one or more panels on this podcast, then you can. No subject matter expertise or podcasting experience is required, and we're always eager to add new panelists. Just email unseenpodcast@gmail.com and we'll get you started. The Unseen Podcast is produced by Paul Carr and is released under the Creative Commons Attribution Share-alike license. Music is by DJ Spooky.